If you only remember one argument from this paper, make it this one. The transformer isn't just a cleaner design. The authors claim self-attention wins on the things that matter in practice. How much computation you do, how much you can parallelize, and how easily the model can connect distant tokens. In this part, we'll go through their three-way comparison: complexity, parallelization, and path length for long-range dependencies. And you'll see exactly why self-attention was the turning point. Let's take them one by one. First, total computational complexity per layer. How much work does the computer have to do to process a sequence? Second, how much of that work can be parallelized? This is captured by the minimum number of sequential steps required. In other words, how many operations must happen one after another, with no skipping allowed. The fewer must-wait steps, the better. Third, the path length between distant positions in the network. When a word near the end depends on a word near the beginning, how many steps must information travel through? The shorter the path, the easier it is to learn long-range dependencies. The authors actually summarize all of this in a single table, and it's worth translating it into plain English. For self-attention, the work grows with the number of token pairs, because every token can look at every other token. That's the quadratic cost people talk about. But the sequential steps are constant. The layer can be computed in parallel. And the maximum path length between any two positions is also constant. One hop. For recurrent layers, the work scales differently. But the key limitation is the sequential part. You need one step per token. So the number of must-wait steps grows with sequence length. And the path length between far-apart tokens grows with distance, because information has to pass along the chain. For convolutions, you can compute a layer in parallel, but each layer only sees a local window. So to connect far-apart positions, you stack layers. That's why the path length depends on how many convolutional layers you need. And finally, the paper notes a compromise: restricted self-attention, where each token only attends to a local neighborhood. That cuts the compute a lot, but it increases the path length because information now has to travel across multiple neighborhood hops. The authors also note that standard convolutions can be more expensive, and that a more efficient variant, separable convolution, reduces that cost substantially. In fact, with very wide kernels, the remaining compute starts to look comparable to what the transformer already does: self-attention plus the pointwise feed-forward layer. Now, let's dive into each of these dimensions in more detail, starting with the most intuitive one: parallelization. Remember back in Part 2 when we talked about the sequential bottleneck? This is where that problem gets addressed head-on. Recurrent layers, like RNNs, have an unavoidable constraint. They process the sequence step by step. Word 1, then word 2, then word 3, and so on. That means you need as many sequential steps as there are tokens. Self-attention does not have that constraint. Within a layer, the computations can be set up so the model processes all positions together in a single parallel pass. Convolutional layers are also parallelizable within a layer. They can process all positions at once, too. This is why self-attention directly addresses the core bottleneck of recurrence. Modern GPUs are built to do many operations at once. Self-attention lets them do exactly that. Think of it like a restaurant. With an RNN, one chef cooks each dish in strict order. 50 dishes means 50 time periods. With self-attention, many chefs work at once. The kitchen tackles the full order together. Now let's talk about the second dimension: computational cost. Self-attention has a cost that grows with how many pairs of tokens you consider, because each token can compare itself to every other token. With 1,000 tokens, that's roughly 1 million token-to-token comparisons. 1,000 times 1,000. For very long sequences, full self-attention can become expensive. But for many common tasks, like sentence-level translation, sequence lengths are relatively modest, while the internal representation size is quite large. In the base model, you might have a few dozen tokens, but each token is represented by a 512-dimensional vector. In that regime, the paper argues self-attention can be computationally attractive compared to recurrent layers. This tends to be true when the sequence length is smaller than the representation dimension, which is often the case in sentence-level tasks. The authors also acknowledge the long sequence challenge and point to an obvious direction. You can restrict self-attention so each token only attends to a local neighborhood, not the entire sequence. That reduces the computation substantially, with a trade-off. You save compute, but you may lose some very long-range visibility. Now for the third dimension, and this is the most important one. Path length. Why does path length matter so much? Because learning long-range dependencies requires information to flow from one position to another. The more steps that signal has to travel through, the more it can degrade. It's like the telephone game. The more people in the chain, the more the message gets distorted. In deep learning terms, this connects to why long chains can be hard to optimize. Signals can weaken as they pass through many transformations. Here's how the architectures compare. First, self-attention. In a single self-attention layer, any position can directly connect to any other position. That means the maximum path length between two tokens within that layer is constant. One hop. So the word it can directly look back at animal, even if they're far apart. Second, recurrent layers. Information has to flow step by step through the sequence. To connect the first token to the 100th token, the signal is effectively passed along through the intermediate steps. The path grows with distance. Third, convolutional layers. A single convolution only connects local neighborhoods. To connect distant positions, you stack multiple convolutional layers. With the right design, you can reduce the number of layers needed, but it's still not the direct global connectivity you get from self-attention. The practical implication: shorter paths make it easier for the model to learn long-range relationships. That's a core reason transformers handle long-distance patterns so effectively. There's also a practical bonus that the authors highlight. Self-attention can be more interpretable than recurrence. You can inspect attention weights and visualize what the model is focusing on. Different heads often learn different patterns. Some focus on local syntax, some capture longer-range links, and some align source and target tokens in translation. This isn't a perfect window into reasoning, but it's a useful diagnostic tool. It gives you more visibility than a typical recurrent hidden state, which is harder to interpret directly. Now let's tie this back to where we started. Remember the promises made at the beginning of the paper? Let's see how they delivered. First promise: reduce the sequential bottleneck. Delivered. Self-attention avoids step-by-step processing within a layer, enabling strong parallelism. Second promise: enable massive parallelization. Delivered. The encoder can process all positions together, and attention operations are highly compatible with GPU computation. Third promise: better capture long-range dependencies. Delivered. Any token can connect directly to any other without relying on long chains. Fourth promise: strong results and faster training. Delivered. The paper reports state-of-the-art translation quality. They report training times of about 3.5 days for the big model and about 12 hours for the base model, both using 8 P100 GPUs. The authors describe this as a small fraction of the training cost of prior best models. In context, training runs around that time were often measured in days, and sometimes longer depending on model and hardware. So those timeframes aren't just a small improvement. They change what's practical. So when you step back and look at what's been achieved, it becomes clear why attention is all you need. Not because attention is a clever trick, but because it removes the constraints that held earlier architectures back. Sequential bottleneck? Dramatically reduced, because recurrence is removed within each layer. Long-range dependencies? Easier to learn. Training speed? Improved through parallelism. Visibility into behavior? Improved through attention patterns. The transformer didn't just tweak RNNs, it changed the default blueprint for sequence modeling. And that brings us to the end of the core journey through this paper. Across parts 1 to 6, we built the full intuition, step by step. In part 1, we saw the motivation. Sequence models were powerful, but slow and hard to scale because of sequential computation. In part 2, we looked at what came before: RNNs, convolutions, earlier attention ideas, and why each helped, but still left a bottleneck. In part 3, we mapped the transformer's big picture, the encoder-decoder stack, and how information flows through it. In part 4, we opened the engine: queries, keys, values, scaled dot product attention, multi-head attention, and the 3 places attention shows up. In part 5, we covered the supporting components that make it train and generalize: feed-forward layers, embeddings, and positional encodings for word order. And now, in part 6, we've seen the core argument for why self-attention wins: parallelism, efficiency, and those short paths that make long-range dependencies easier to learn. If you stop here, you already understand the ideas that changed the field. But here's what happened next. The transformer became a standard building block for modern language models. BERT popularized the transformer encoder for language understanding. GPT popularized the transformer decoder for language generation. And countless systems since have built on the same core design. So when you use a modern language model today for writing, coding, translation, or search, you're benefiting from ideas introduced here. But the paper doesn't just argue, it proves. So next, in part 7, we move from why the transformer should work to how they made it work in practice.